Today we'll be talking about how we're connecting awkward array into the other component, and not the other components, but some other components of the PyData ecosystem. So let's get started here. So brief outline for the things we're going to cover today. So we'll start with the components being awkward array, of course, and then beyond that, we'll talk a bit about dask and pandas because we will make new connections between awkward and dask as well as awkward and pandas. And finally, we will wrap up with demos for however much time we can fit in at the end of the presentation. Okie doke. So first, let's start talking about awkward array. So awkward array is a library to operate on nested variable size data. This sentence here is straight out of the README for awkward array. So folks that have used the PyData ecosystem should be quite familiar with NumPy. The paradigm of array programming is very powerful. It's very powerful in Python. And packages like NumPy are great for operating on rectilinear data sets. And you have a wonderful user experience there. So awkward array brings that same user experience to being able to operate on nested variable sized data. That's the new feature that awkward array allows you to analyze nested data. So we'll have a small example here to really show how this works. So here I'm creating an awkward array. This awkward array is of length 3, but each of the elements of this length 3 array it's another list. So here we have a essentially list of lists, but inside of the first element of the array, we have some number of records, and the records have an X and a Y field. And inside of the Y field, we have another list. So you can see this nested data structure here. The second element of the array is empty, and the third element is another list of these records. So NumPy-like idioms, we can operate on this array with similar syntax as we would with NumPy. So in this line here, I'm accessing the Y field of the array, but keeping the dimensionality. And then once I get to the innermost dimension for the Y field, I want to take everything past the first element. So this will look like so. We keep our length 3 array here, but inside we continue to have the lists as each element of the outer array. And then we go into the Y field and we take all but the first element. So you can see, I mean, this is a not a super long code snippet, but we're doing something relatively technical to go in and take the square of what we get from this slice. And so if we take all but the first element of all of our Y inner lists, of course, the first one is empty. Then we have the 2 squared is 4, and 2, 3, 9, and so on. So we're able to operate on this nested data structure as we would with array programming with NumPy. So that's a little example of awkward array. So just like NumPy, arrays are dynamically typed. So you have all the power of making an array as you would like to in a dynamic programming language like Python. But when you go to actually execute the operations on them, these operations are compiled. So you get that performance. This is really the power of NumPy, but awkward array has done something very similar, but for these nested data structures. Okay, the next component for the subjects of today will be dask. So dask has been spoken about at PyData already, but brief intro, dask provides both a task graph library and schedulers to execute those task graphs. So plugging awkward into the broader ecosystem, dask is part of that broader ecosystem. It's been around since about 2015, so it's been a member of PyData for some time now. So the task graph library components of dask. So what dask allows you to do is write code that looks very similar to the code you would write for eager programs, but what dask is doing is it's creating a task graph that will be lazily evaluated. So the eager program NumPy, then we can, the equivalent on dask side is dask.array. So with the dask.array API, you can do NumPy-like programming to create executable task graphs. Same thing for pandas to dask.dataframe, Python iterables, so lists and things to map to dask.bag. And then there's also dask.delayed, which allows you to write custom applications. So the main idea here is write programs in a way that one is familiar with, but don't execute the math that you're writing. Just build up that task graph so that you can then execute it lazily. So this works because Dask collections are partitioned versions of those concrete types from the eager programs. So a Dask array is just it's a chunked NumPy array. You have a bunch of small little NumPy arrays, not necessarily little, but smaller NumPy arrays than your overall Dask array. And the Dask array represents those, and the execution engine orchestrates how to compute with them. So that's Dask in a nutshell. So a small example here to show going from NumPy to Dask, we can create an array of ones, 1000 by 1000, and take the sum along one of the axes. So this is each of these lines is going to immediately execute something. In the dask.array version, it looks very similar to NumPy. We call a ones function to create a task graph that will give us a 1000 by 1000 array. We tell it the chunks that we'd like, so how to partition it, and then we call the sum. It looks very similar. The sum function along the first axis, but the main difference is with NumPy, this is going to immediately execute the sum calculation. With Dask, this is going to add to a task graph. It's going to stage the computation of the sum. So we don't actually get anything until we call compute. And calling compute is when we send the task graph over to the execution engine, which I'll talk about now. So very briefly, the execution engines for Dask include both the threaded scheduler, something you can spin up on your laptop to use all of your resources. So this allows you to parallelize operations, but also if you have a large data set that doesn't necessarily fit in your laptop's memory, if you chunk it and operate it on pieces with the task graph, it becomes more tractable. Then there's also the distributed scheduler, which allows you to scale up to any number of machines. You can go to the cloud. There was a talk at PyData this year by Matt Rocklin, where he discussed how to spin up Dask on clusters. Okay, so the last component before we start making connections that we'll talk about here is pandas. I don't probably need to talk about pandas too much here at PyData. It's a foundational package for the PyData ecosystem. And many folks that use Python to do data analysis, pandas is their first exposure to that. So very briefly, pandas is for columnar analysis on data frames. So you have some number of columns. These are one-dimensional series of scalar types, typically. So a column of floats, a column of ends, of strings. And multi-dimensional is possible, but it's not as nice as if you have scalar columns, and it relies on Python's object type. So it's a little more complicated than just dealing with rectilinear data. So a small motivating example for the connection between awkward and pandas is if we have a data frame here, two columns, A and B. A is some set of integers, but B is some set of lists. So we have some variable length thing in our B column. So if we go and access the B column, we see that we have an object type. So this is a list. And if we try to do a pandas operation on this, like take the mean of the series, it won't work because this is a list. So there are ways around this, kind of beyond the scope of this presentation today. But what I'm getting at here is it'd be nice to have kind of immediate support for nested structures like this. So the way to go about doing that is with extension arrays and types. So I'll talk about real briefly here while we're talking about pandas. So pandas has built-in support for adding additional types of columns. So as I mentioned, there are already existing floats and string kind of thing. There are things beyond this, but there are built-in types to pandas that work really well. And Pandas allows you to extend on these. So we'll end up talking about that. So I just wanted to mention the existence of the extension array and dtypes interfaces for Pandas. So what is new? The things that we've created. We will start with awkward plus dask. So if you remember the table I showed a few slides ago, we had 4 entries in the table, and now we are adding a 5th with dask-awkward. So dask-awkward adds a new task graph creation API that does the same thing that NumPy to dask array and pandas to dask data frame. They map the eager programs to a new, to a lazy version with dask. Dask-awkward does the same thing for awkward array. So we have a new task graph creation API, and we have a new collection. We have a partitioned awkward array that that allows us to use all of the heavy work that's already gone into Dask. So the reason why I wanted to talk about the execution engines is because by making dask-awkward like the other task graph creation APIs, like dask.array, like dask.dataframe, following that interface, satisfying that interface, we get the execution engine for free. So the execution engines are the part of Dask that really aren't the topic of this talk, but because we've plugged into Dask in a way where we're speaking Dask's language, we benefit from Dask's execution engine just by making the Dask array library. The other new component is awkward plus pandas. So we've created a new extension array and dtype, the awkward extension array and the awkward dtype, and these allow native use of awkward arrays inside of pandas objects. So this this makes the nested structures something that we can stick into a column in pandas. And we also have, along with the extension array and type, we also have what in pandas is called a series accessor, which allows us to go one level deeper even when using pandas workflows and actually use the awkward library itself from a pandas object. So I'll show these with a small example here. So we have here a series. This is the same series that I showed in that previous little example, where in this series we have a list of lists essentially. And if we import awkward pandas, we can convert this object, this set of lists, into an awkward array, which, remember, compiled operations on these dynamically typed objects. So it will be faster than just a Python list. And also, on top of that, we get to take advantage of Awkward's computation engine. So here, remember, if we tried to call mean on this series before, we got an exception was raised. But now, if we take the mean, we get a result. It actually takes the mean of this column as if the data got flattened. So this is the case here is taking the mean of 1, 2, 3, 4, 5, 6, which is 3.5. But we can also, as I mentioned, go one step deeper and actually use the awkward library. Awkward has a mean function that allows you to provide an axis. And what this does is it's going to take the mean along that first inner axis, which is going to be the mean of 1, 2, 3, which is 2, the mean of 4, which is 4, the mean of 5, 6, which is 5.5. And it will actually return a series back. So we're staying in pandas world. we're sticking with pandas objects, but we're able to use the awkward library and execute these operations on a pandas series. So that's a small example for combining Dask and awkward. Sorry, pandas and awkward. Okay, so before I jump into the demos, I did want to mention briefly that you can start using these today. So first official releases for dask-awkward and awkward pandas are coming out this month, because we've been collaborating with the developers of awkward array, and there's a new major version of awkward that's going to be released, and along with that, these new libraries. So you can install these today. There are pre-releases available on PyPI, so you can pip install them. And the first official releases are right around the corner. I did just want to mention that right here, just in case I can't come back to this because I wrap up with some demos. So I will jump over to the first demo here. Make this a little bit bigger, if I can. There we go. I'm gonna have to do this manually. That's okay. Okay, so I have a notebook here, and what I'm going to do is I'm going to import dask-awkward and awkward. The task that I'm going to investigate here for this demo is I'm going to be looking at some Chicago taxi trips. So I'm going to load in some data here inside this Chicago data set. I just have a bunch of Parquet files over here, just many 25 Parquet files. This data set is about a little less than a gigabyte maybe. So it'll be good for a demo. So the first line here, I'm using dask-awkward and reading from Parquet. This is going to start creating a lazy task graph, but just for some demonstration purposes in the demo today, I'm also going to load straight from awkward one little 1/25th of the data set. So I'll execute that. So that was very fast. The longest time was actually spent in loading it eagerly. So let's look at our lazy data set. So we have a dask-awkward array with 25 partitions. We can start to investigate a little bit. We can look at the fields inside the data set. There's trip information, payment, company. Inside of trip, we have some more information, time, the distance, things like that. But we can look at the total set of columns that were found. So trip has some nested information, payment has some nested information, and company is some scalar piece of information. Using the eager data, which I preface with an underscore here, we can look at the structure with a little more detail. So inside of trip, I have time, distance, and also in a beginning longitude and latitude and time. We also have the end information as well as some list of points along the path that the trip took, and then information about the payment. So we have really the point here is we have nesting. we have nesting and variable length pieces of data. So I will look at one trip individually that I know has some data in it. So you can see here, every trip has an individual start and stop and stuff. But then there's this list of differences in longitude and latitude. And so that's how we get different points along the path. So this is the data set that we have that we want to try to figure something out using dask-awkward array. So we can look, now going back to our non-underscored data set, this taxi by itself, we can look at the 0th element of the array without computation and actually get a little bit of information out of it from this underscore meta attribute. So this will tell us that we have some, we don't know how long, array of trips inside here. So what this is telling us is the 0th element of our taxi data set is one taxi. And that taxi has some variable number of trips. And inside the trip, inside each trip is some variable number of steps along the path. So let's see if we can calculate the distance that each path, the distance of each trip using these path differences. So first, I will do a broadcasting operation. So the trip's beginning longitude, this is just one number, but the longitude differences, that's a variable thing. We don't know how many points along the path got saved. And so we can do this with all longitudes and latitudes. And then here, because this is the Chicago data set, we can convert to kilometers to make this a little bit more usable. And this is still just building up. You can see these cells are executing immediately. I'm operating on my dask-awkward collection, but no calculations are happening yet. We're just building up a task graph. So we can calculate the distance of these trips using a non-array programming style, right? Because we've got this nested structure, our first inclination may be to go and write loops. So here's some pseudocode for how this would look in a loop. We'd loop over all of our taxis, loop over all of the trips for each taxi, and then we'd start calculating some lengths. So we'd look at in the trips paths, we'd take the, I plus 1 minus I points along the x and y directions, square those differences, take square root, and this would build up the length for a trip. But we could do this with array programming. So I've written it out here in 3 lines. So we're taking our horizontal and our vertical distances. So we're taking all taxis, all trips, take all points but the first, subtract those from the same thing, but all points but the last. And so this doesn't care about how many points there are along the path, but it's still array style programming. And so if I do this with horizontal, the x distance, the y distance, and then take the square root, and then finally sum it all up for each trip, because I'm taking an inner axis here, this is array programming with an unknown set of pieces of nested data. So we could have written this all in 1 line, but to make it a little bit more readable, I split it into 3 here. And if we execute this, it's immediate. All we're doing is staging more calculations. And so we can look to see what our lengths may end up being. It's going to be some array of floats but remember, we have trips per taxi. So we have some number of taxis, some number of trips, and then each trip has a length. So this is really going to be an interesting task graph to visualize. So it's a little busy here. We have 25 partitions, but you can see all these steps that we built up. We're reading the data, grabbing information from the trip, grabbing information about latitude and longitude differences, doing a subtraction, a multiply, more accessing of the data. So this is our task graph getting built up. So let's say we want to see a comparison between the distance that we've calculated for the trips and also some recorded distance that was recorded like by the driver there when they made the trip. We can make a histogram. So here I'm plugging into another, we can make a histogram to look at this comparison. So I'm using another dask library, dask histogram. And what I'm doing is I'm taking my lengths calculation along with the trip distance that was recorded when the trip was taken. And I'm going to make a 2-dimensional histogram so we can look at it. So but because I'm using another dask library to make this histogram, it's also just a very quick thing. We're just building up the task graph. So now let's take another look. Now that we've added a new step, you'll see that we have all of our previous steps, but now we've added a histogram step. So we're getting this aggregate, this reduction and aggregation here. Finally, we're on each partition of our data set, we're making a histogram and combining it with the histograms on the other partitions to finally get the last piece of data that we'd like. So I can also show one more interesting thing about this calculation, and that is Dask has optimizations to make this task graph, to try to simplify the task graph some. And so by writing dask-awkward in a way that in Dask language, we benefit from this already. So we can optimize this task graph, and we can already see that so many of these steps can happen on the same node in a task graph. So we see this huge collapsing of these embarrassingly parallel parts into a single node. So reading data off disk and performing the calculations, Dask is able to optimize where the computation happens. So we go ahead and see what we want to see here. We can look at our histogram. So I made a little progress bar. I'm just executing this using all the threads in my computer. So right now I'm reading all the data off disk. Okay, and moving on, and it's starting to do some of those math calculations. And then, depending on which chunk of data got read first, maybe I already made my first histogram at this point. I'm not sure. But then here we go. The computation is done, and we can look. And here's our trips. So along the x-axis here, we have our computed distance. Along the y-axis, we have the recorded distance. So you can see most of them line up. They're 1-to-1. But there are a few little blotches in the data set that maybe could warrant some further investigation, but we don't have time for that today. But this is just one little demo of using dask-awkward. So in the last couple minutes, because I do want to leave a little bit for questions, I want to show awkward-pandas. So here, I'm going to be looking at a particle physics data set. I've got a little shout out to the particle physics community because they are the ones behind awkward array, and I used to do some particle physics. So the thing I'm going to do here is read in a data. I'm going to import awkward pandas, those pandas and awkward. I'm just going to go ahead and read in my awkward data set. So here I have an awkward array. I can look at it real fast. I have some nested data. I'll say a few more things about this in a second, but I'm going to go ahead and convert this into an awkward series. And I'm going to name that series nested. This is what one row of the series looks like. These are some events in a detector. So there's the detector run, the event number, which span of event taking of data collection was happening. But then we have information about the particles that were seen in the detector. But there's some variable number of muons in this data set. We don't know how many muons of one particle that can pop up in the detector, and each event can have 0 muons, 4 muons. We don't know, and those muons have different properties, their trajectory. So this data set has nesting. So we can look at our series, and yeah, you can see there's some nested information in here. But what we can do is we can use awkward pandas to unroll this into a data frame, but with this 2 columns method on our accessor. And what this does is it converts the scalar things into regular columns, but keeps the nested structure that it couldn't convert into a standard pandas column. It keeps that in an awkward column. So we can look at our data frame now. And so now if you can start using run, luminosity block, event, you can start using those as you normally would in a pandas workflow. And so you can go in and see that we have a regular pandas series here. And there's also the ability to jump down lower level into the data itself. We can actually get down to the awkward array by passing down from the nested column into its values, into its data. And so we're getting to use pandas workflows, but have all of the power of awkward and still be able to dig into our awkward data if necessary. So we can make a series that's just the muons component of our data set. And one thing that we could figure out is how many muons we have. So the old style would be taking the length of each muon row and looping over the muon column. So this takes a little while. It's still running, still running, still running. Because we're doing a Python for loop here, but we could use, it just finished, but if we use the awkward accessor, we can use an awkward num function along that inner axis to get an immediate result. And they are the same. And we have a muon, total number of muon series. So we could then use that by adding a new column to the data frame. So now we have a new column here. We could limit ourselves with dataframe.query to only those with 2 events. And then we can make sure our data frame only has when n muons equals 2. And finally, we can apply a function to the nested piece using the awkward accessor to make a histogram. And there's, for anybody in the audience that does know the Z boson, there's the Z boson peak. Okay, so I rushed to the end of that demo there a little bit because I did want to leave 2 minutes for questions, but that's it. And I'll jump over here one more time just to say thank you for attending. There we go.
Thank you, Doug. Let's give it 1 minute to see if there's any questions. You have certainly cut it quite close in terms of questioning time.
Yeah. I'll have to jump over to Discord.